right, it's recording. Well, welcome to this TAC meeting on deck management research. This is an opportunity for us to hear a presentation from Dr. Guthrie and his student Tenley from BYU on the multi-year research project that is culminating now. And so we're excited to hear or see the presentation. Also, just a reminder, we received a combined chapters report recently that was distributed to the group. I guess we could say it's for review, but most of it was seen before. It should have been seen before in previous versions of those chapters. This was just an opportunity to see them all together, and in the revised version, probably not their final version, since BYU is still doing some edits. But if you have more feedback on those, on that version, feel free to send those to Dr. Guthrie, and they'll incorporate as much as they can. And you can bring them up in this meeting as well. So, all right, without further ado, I think we'll just press forward into the presentation. I think it will go about 45 minutes, sounds like, and then we'll transition to more of a Q&A and discussion on the research and implementation of the results. So we'll turn it over to Spencer and Tenley.
Okay, I'm going to present my screen. Hopefully this works. I've never actually used Google Meets before, so should.
Well, yeah, it should work. It's one of the simplest platforms, but it's also one of the drawbacks that it's so simple sometimes.
Okay, so does that show?
Yes.
Okay. Perfect. So the title of the presentation and the report is Development of a Management Guide for Concrete Bridge Decks in Utah. So for an outline of the presentation, I'll first give a brief introduction. I will remind everyone of the objectives, and then I will go through each objective, which was literature review, bridge deck testing, and then the bridge deck management guide, and then we'll give some conclusions and recommendations at the end. As an introduction, Utah, we know, has severe winter weather, and because of that, we are required to salt the roads, and as the chloride ions diffuse through the concrete above the rebar and around the rebar, they cause corrosion to initiate once a corrosion initiation threshold is reached. And the corrosion leads to tension in the concrete, which then cracks and spalls and creates potholes, which are not safe to drive over and can lead to structural issues in the deck as well. So with that in mind, the objectives of this research: the first objective was to investigate bridge deck condition assessment methods used in the field and laboratory, methods of managing bridge decks, and methods for estimating remaining bridge deck service life using computer models through a comprehensive literature review on these subjects. The second objective was to collect and analyze field data from representative concrete bridge decks in Utah. And the third objective was to develop a concrete bridge deck management guide for Utah. So the first objective, bridge deck condition assessment methods used in the field and laboratory, methods of managing bridge decks, and methods for estimating remaining bridge deck service life using computer models were investigated through a comprehensive literature review on these subjects. So first, condition assessment methods. Before an informed decision can be made about a preservation treatment, rehabilitation treatment, or reconstruction, the condition of the bridge deck must be known. Various methods, both destructive and non-destructive, are available to evaluate the condition of a bridge deck and determine appropriate preservation, rehabilitation, and reconstruction actions. And in this research, 23 condition assessment methods were investigated. For each method, we described the theory supporting the test or method, the procedures for the test or method, how to interpret the data, and then just some other considerations. And so those were done for each and every tool. I'm not going to go through every single one of those in this presentation, but they can be found in the report in Chapter 2. So this is a summary of each of those test methods. You can see the 23 there, whether they are destructive or non-destructive. A majority of them are non-destructive. And then just a brief description of the factor that is evaluated, and then we ranked them according to equipment cost, data collection speed, required expertise, and then whether or not traffic control is required. And in this, if there were multiple methods, as long as there was one that did not require traffic control, we said no. Otherwise, any method requires it. After the condition of a bridge deck has been determined through the appropriate assessment methods and tools, the proper preservation, rehabilitation, or reconstruction method can be determined. And first, for preservation rehabilitation, the FHWA defines bridge preservation as action or strategies that prevent, delay, or reduce deterioration of bridges or bridge elements, restore the function of existing bridges, keep bridges in good condition, and extend their life. Adding a surface treatment to a concrete bridge deck is an effective and economical method of reducing the ingress of water and chloride ions. Although the properties and performance of these products can vary, the products are usually intended to serve as barriers to the ingress of both water and chloride ions. And the FHWA states that rehabilitation involves major work required to restore the structural integrity of a bridge, as well as work necessary to correct major safety defects. And rehabilitation generally involves higher costs and more work than bridge deck preservation. Removal and replacement of deteriorated concrete is a common motivation for rehabilitation. This figure shows that careful management can extend the life of a bridge deck with strategic preservation and rehabilitation actions. You can see that the solid black line is just an average baseline deterioration curve for a bridge deck. But if we were to apply preservation treatments early in the life and subsequently at regular intervals, then we can extend the life of the bridge deck. And the same with rehabilitation. Although if we wait longer before we do any sort of a treatment, then we don't get as much of an extension of life as we would if it was carefully managed using preservation treatments from the beginning of its life. So for the bridge deck preservation and rehabilitation methods, our research, we had 6 bridge deck preservation and rehabilitation methods that were investigated. And again, for each method, we reported the theory supporting the method, considerations, procedures for the method, and benefits of the method. And these methods are shown in this table along with unit costs that we received from UDOT. And then the expected treatment service life in years comes from either the observations that we made during field testing or from the literature. And each treatment also addresses a specific factor, varying from just cracking and concrete quality, meaning keeping chloride ions out, all the way to construction quality, meaning closer to like cover and protection of the rebar and delamination. And we included a typical full depth cast in place concrete deck replacement down at the bottom, just as kind of so that you can see the difference in price that preservation makes.
Can we real quick?
Sorry, go ahead.
On the scarification overlay, what overlay is that referring to? I was just looking at your costs and your life.
Concrete overlay, so just replacing with concrete.
Okay, thank you.
Yep. For bridge deck reconstruction methods, 4 non-conventional bridge deck reconstruction methods were investigated. And again, we reported on the theory supporting the method, considerations, procedures for the method, and benefits of the method. For estimating remaining service life using computer models, that is another important aspect of maintaining a network of bridge decks. And a primary method of estimating remaining service life involves the use of chloride concentration profile modeling. These models can simulate the effect of equilibration after sealing the surface with an overlay, ensuring that the chloride concentration at the depth of the top mat of rebar never reaches the chloride initiation threshold. And the effect of removing chloride-contaminated concrete and replacement with new uncontaminated concrete, so like a scarification and overlay, is, as is the case can be simulated, ensuring that the chloride concentration at the top mat of rebar is reduced to a level below the chloride initiation threshold after equilibration. And the software can also be used for predicting the time interval from construction to the initiation of corrosion, predicting the time interval from initiation of corrosion to the time of the first repair, or the time at which an acceptable damage level is reached, determining the repair schedule for the life of the structure, and or estimating life cycle costs. And there are a lot of different software programs that can do these. We did not specifically go into each individual model or software, but we just kind of gave a general report on how these work. Now, the second objective, field data from representative concrete bridge decks in Utah were collected and analyzed to investigate the effects of selected bridge deck features, including polymer overlay application, deck age at polymer overlay application, overlay age, asphalt overlay application, both with and without a membrane, stay-in-place metal forms and their removal, internally cured concrete, and use of an automatic deck de-icing system. So we selected, with input from UDOT, 15 different bridge decks, 5 of which had bare concrete surfaces, 5 of which had asphalt overlays at the time of testing, and 5 of which that had polymer overlays at the time of testing. Some of the statistics about each, or I guess information about each bridge deck, is shown in this table. You can see that a majority of the decks had epoxy coated bar. And the reason that we selected each is in the very far right column. And those kind of come into play in just a little bit. For bridge deck testing, we laid out the site first and determined the coordinates of 8 testing locations on each of the 15 bridge decks. And we used a set of 6 random number pairs and the same random number pairs were used on each bridge deck. And we multiplied the length of the bridge by the longitudinal random number and the width of our testing area, which varied. And we multiplied that by the transverse random number. The test locations 1 and 2 were co-located, and also 7 and 8 were co-located. And that was so that we could drill a chloride hole directly over the bar for test location 1, and then within a few inches between the bars for test location 2, and then 7 was between bar and 8 was over bar. And that was so that we could determine the effect of the physical presence of the bar on chloride concentration. The testing included cover depth measurement, chloride concentration testing, chain dragging, half cell potential testing, Schmidt rebound hammer testing, impact echo testing, and VEI testing. These 4 photos show from left to right cover depth measurement, chloride concentration sampling, chaining, and half cell potential. And then again from left to right, Schmidt rebound hammer, the impact echo machine, and VEI testing. And the results of that bridge deck testing is shown in this table. These results show averages from all of the locations, well, from locations 2 through 6. So the chloride concentration data here does not include data that was collected over the bar, but just between bars at every location. And there were some decks that we either had issues with the equipment or did not measure some of these values, like the relative energy of echo. We didn't do impact echo on the decks that had asphalt overlays. And moving on with some more specific results, we used the chloride concentration data at the depth of the top mat of rebar for all of the bridge decks that had epoxy coated bar, and we correlated that with the percent of samples that were delaminated, and we found that there were no samples that were delaminated until the chloride concentration was at least 8 pounds of chloride per cubic yard of concrete. So these data support the possibility for epoxy coating reinforcing steel to withstand chloride concentrations up to 4.6 times higher, than the uncoated reinforcing steel before corrosion is initiated. So from this research, we recommend a corrosion initiation threshold of 8 pounds of chloride per cubic yard of concrete for bridge decks with epoxy coated bar. And since there were only 2 decks that had black bar, insufficient data were available in this study to independently evaluate the typical corrosion initiation threshold of 2 pounds of chloride per cubic yard of concrete for black bar with respect to the occurrence of delamination. And for collecting the chloride concentration sample above the bar versus between the bar, the figure on the left shows the ratio of the chloride concentration above the bar to the chloride concentration between the bar, plotted against the chloride concentration between the bar. So you can see that for chloride concentrations between 0 and 15 pounds of chloride per cubic yard, a majority of the points are above 1, and the regression line is also above 1, meaning that there are typically more chlorides that accumulate above the bar and immediately around the bar than there are when you sample between the bars. So when you would sample between the bars because you can get a deeper sample and you don't have to worry about specifically hitting the bar and causing any damage to the epoxy coating or to anything like that. So when you sample between the bars, you need to adjust that chloride concentration up by 40 to 70% to represent the actual chloride concentration immediately around the rebar. And the figure on the right just plots that regression line for a ratio of 1.4 to 1.7 and shows where it corresponds to 2 pounds of chloride per cubic yard of concrete, which would be the chloride initiation threshold for black bar. We did some statistical analyses using the results of the bridge deck testing. 2 sample t-tests were performed to investigate the effects of selected bridge deck features, including polymer overlay application, deck age polymer overlay application, overlay age, asphalt overlay application, both with and without a membrane, stay-in-place metal forms, stay-in-place metal form removal, internally cured concrete, and use of an automatic deck de-icing system. And specifically, the comparisons were considered only when the deck ages at the time of testing were different by less than 5 years, and all the primary features of the bridge decks were similar except for the feature of interest. A 2-sided p-value was used to determine if the selected bridge deck feature had a significant effect on the measured properties. A p-value less than or equal to 0.05 was used to establish statistical significance at a 95% confidence interval. And in these 2 sample t-tests, we were able to have 11 comparisons that involved all 15 decks. And in each comparison, the null hypothesis was that no difference existed between the 2 bridge decks, and the alternative hypothesis was that there was a difference between the 2 bridge decks. And this table summarizes the results of all of those statistical analyses. In the report, we have a discussion about each one that involves some more data. But for the purpose of this presentation, we just wanted to summarize this into one single table. And one thing to note is that although half-cell potential was significant in a lot of the comparisons, it didn't always follow the correct theory or what we would expect to find. And the reason for that is most likely due to either zinc in electrical contact with the half-cell system, or possibly the epoxy coating on the rebar. The ASTM standard for half-cell does not recommend that you do half-cell testing with decks that have epoxy coated rebar. But the main findings from each of these comparisons, when looking at a deck with and a deck without a polymer overlay, we found that placing a polymer overlay immediately after deck construction is an effective practice for preventing chloride ion ingress, while waiting 5 or more years is most likely too late to prevent the chloride-induced corrosion. And when we looked at F738 and C931, both decks had polymer overlays that were placed immediately after deck construction, but one was older than the other. And we found that a higher overlay age does not have a measurable effect when both treatments are in good condition. We found again that placing an asphalt overlay with a membrane immediately after deck construction is an effective practice, while waiting too long is not effective and is typically too late to prevent the chloride-induced corrosion. We had a deck that currently had stay-in-place metal forms and one that did not. Is that right? Am I looking at that one right? Oh, we compared to decks that currently had stay-in-place metal forms and decks that had them removed after 18 years of life, and we found that there was no statistically significant difference in those two, between those two decks. Oh, go back. And when we compared the two decks that were out at Mountain View Corridor, F800 and F799, we found that bridge deck construction using internally cured concrete is not an effective practice for protecting against rebar corrosion. We found no statistical difference between those in terms of chloride concentration. And then a kind of unique comparison was C759 and C757. And C757 had automatic de-icing system in place. And we found that automatic de-icing systems can lead to higher chloride concentrations at typical cover depths, which can in turn lead to increased corrosion potential. Moving on to the third objective, a concrete bridge deck management guide for Utah was developed. The data from bridge deck testing were supplemented with information about current bridge deck management practices and treatment costs obtained from UDOT, as well as information about condition assessment and expected treatment service life reported in the literature review to develop a decision tree for concrete bridge deck management. The decision tree includes 10 junctions labeled A, B, C, etc., and 7 recommended treatments labeled 1, 2, 3, etc. The junctions require the user to address questions about surface type, degree of protection against water and chloride ion ingress, degree of deterioration, and years of additional service life needed. And the answers to each of these junctions or each of these questions lead to selection of treatment options ranging from repairing an overlay to full depth bridge deck reconstruction. So we've broken out the decision tree into a few different figures just because it's too large to show on one screen. So moving through, just starting at A, we first ask, does the bridge deck currently have an overlay? And then we ask about the chloride concentration at the top mat of reinforcement. And then we ask about equilibration of the existing chloride ions and whether or not there can still be initiation of corrosion. And then if a more thorough treatment is needed, then we ask how many additional years of service life are needed, because we don't want to recommend a very expensive treatment if there are plans or there's a possibility that the deck will be rebuilt in the next 5 years anyway. Otherwise, we can look at options from 5 to 10 years or greater than 10 years. And if we want greater than 10 years, then we look at what percentage of the deck surface is delaminated, patched, and or potholed. And based on that data, we can either have scarification and overlay, a partial depth deck replacement or a full depth deck replacement based on the percentage of the underside of the deck that has deterioration and what the chloride concentration at the bottom mat of reinforcement is. If the deck has an overlay in place already, then we ask if greater than 90% of the deck area is protected by the overlay or membrane. And if it's not, then we basically just treat it as a bare deck and go from there. And then if it is, then we look at the chloride concentration and whether or not equilibration is possible. So moving through each junction, Junction A involves using visual inspection or inventory records to determine the bridge deck surface type. Bridge decks with overlays are then evaluated in the decision tree differently than bare concrete bridge decks. Junction B involves using chloride concentration testing to evaluate the chloride concentration at the top mat of the reinforcement. And chloride concentration sampling should be performed to a depth just below the bottom mat of reinforcement to also enable evaluation of the chloride concentration at the bottom mat as potentially required for Junction G. So we don't want to just sample a few inches down and then get later in the decision tree and not have enough information to complete the treatment option. And as we discussed earlier, chloride concentrations collected between rebars should be increased by 40 to 70% to better estimate the chloride concentration of the concrete in direct contact with the rebar. And corrosion initiation thresholds of 2 and 8 pounds of chloride per cubic yard of concrete should be used for decks with black and epoxy coated bar respectively. Junction C involves using chloride concentration testing to determine the chloride concentration profile and computer modeling software to evaluate the possibility of corrosion initiation in the future. So even if we were to seal the deck right now, let's say the chloride concentration at the top mat is not currently high enough to initiate corrosion. If we were to seal the deck right now, what would happen over the next 5 to 10 years as equilibration happens? And removal of contaminated concrete may be required to reduce high chloride concentrations near the surface and prevent corrosion initiation after equilibration. And computer modeling software can also be used to simulate this situation. And again, chloride concentrations should be adjusted to better estimate the chloride concentration above the bar, and corrosion initiation thresholds of 2 and 8 should be used. As an example, at Junction C, the chloride concentration profile may be such that the chloride concentration at the top mat of reinforcement is not yet higher than the corrosion initiation threshold at the time that an overlay is placed, but will later exceed the threshold when chloride ions in the overlying concrete nearer the surface diffuse downwards over time as equilibration occurs, even though the overlay prevents new chloride ion ingress. So in this figure on the right, the gray line that goes horizontal represents the rebar at a cover depth of 2.5 inches, and the red dashed line represents the corrosion initiation threshold for black bar of 2 pounds of chloride per cubic yard of concrete. The blue line shows the chloride profile before treatment, and then the simulation assumes that the surface is sealed and no new chloride ions are enter into the system. But after 5 years, you can see that we're already approaching the chloride initiation threshold at the level of the bar, and then at 10 years, we do in fact exceed that at the level of the rebar. And so this needs to be taken into consideration before deciding what treatment should be done. As another example, the chloride profile may also be such that the chloride concentration at the top mat of reinforcement will never reach the chloride initiation threshold even after chloride ion equilibration. So depending on the chloride profile, it may or may not reach the threshold after equilibration. And in this case, you can see that it was not beforehand, and it remained below the threshold for more than 10 years. Junction D involves indicating how many additional years of deck service life are needed. The number of additional years of service life that are needed can be informed by asset management plans developed for a given corridor in which structural, functional, and political aspects of bridge management may be considered. A more expensive and complex treatment is typically required for a greater extension in deck service life. Junction E involves using visual inspection and delamination surveys to evaluate the percentage of the deck area that exhibits delamination, patching, and/or potholing. While windshield surveys may be suitable for some decks, other decks may warrant a more detailed visual inspection, possibly even requiring lane closures. Delamination surveys can be conducted using chain dragging, GPR scanning, hammer sounding, impact echo testing, and/or infrared thermography scanning. Under some circumstances, such as when the overlay has been in place for several years and localized deterioration of the overlay has led to corresponding deterioration at the same locations as the overlay deterioration, VEI results can be substituted for delamination data on bridge decks with asphalt overlays. Since it's difficult to get delamination data on asphalt overlays, there are some instances that VEI can replace that data. Junction F involves using visual inspection to evaluate the percentage of the area of the underside of the deck that exhibits deterioration. Signs of deterioration include cracking, efflorescence, staining, and spalling. Deterioration of the underside of the bridge deck can be a predictor for especially the occurrence of blow-throughs during hydrodemolition. A deterioration threshold of 10% is recommended to avoid extensive blow-throughs and to differentiate between partial and full-depth deck replacement. Junction G involves using chloride concentration testing to evaluate the chloride concentration at the bottom mat of reinforcement to differentiate between partial and full-depth deck replacement. So if the chloride concentration already exceeds the initiation threshold at the bottom mat, then we would use full-depth deck replacement rather than partial depth. And again, as with the top mat, we should increase the chloride concentration by 40 to 70% when we collect between the bars to better represent that around the bar. Junction H involves using VEI or visual inspection to evaluate the percentage of a bridge deck protected by an overlay or membrane. VEI is preferred because some overlay deterioration cannot be determined using visual inspection. And when less than 90% of the deck area has an impedance magnitude greater than or equal to 4.0, the deck should be treated as if it were a bare concrete because the overlay is not protecting enough deck surface for it to be considered as protected. Junction I involves using chloride concentration testing to evaluate the chloride concentration at the top mat of reinforcement to determine the average chloride concentration profile. Chloride concentration sampling should be performed to a depth just below the bottom mat of reinforcement to also enable evaluation of the chloride concentration at the bottom mat as potentially required for Junction G. And again, the chloride concentrations collected between rebars should be increased, and the thresholds of 2 and 8 pounds should be used. If the chloride concentration at the top mat of reinforcement is higher than the corrosion initiation threshold, then the deck should be treated as if it were bare concrete, and you go back to one of the earlier junctions that we've already talked about. Junction J involves using chloride concentration testing to determine the chloride concentration profile and computer modeling software to evaluate the possibility of corrosion initiation in the future. And the same examples that I showed for Junction C regarding chloride equilibration also apply here. Moving into the treatment recommendations from the decision tree. Treatment recommendation 1 is when there is no overlay and there are low chlorides, it has not already exceeded the chloride initiation threshold. And this treatment involves placing an overlay to prevent water and chloride ion ingress. Overlay options include high molecular weight methacrylate sealants, thin-bonded polymer overlays, polyester polymer concrete overlays, and membrane systems with asphalt overlays. In addition to the cost and service life information, traffic levels and surrounding pavement types should be considered when selecting an overlay. So hum-wum sealants are typically best suited for bridge decks with low traffic, such as non-highway bridges. Thin bonded polymer overlays are typically best suited for bridge decks with medium traffic, such as non-mainline and rural highway bridges. And PPC overlays are typically best suited for bridge decks with high traffic, such as urban highways and freeways. Membrane systems with asphalt overlays can be used for any traffic level and are typically best suited for bridge decks whose surrounding pavement is asphalt. Treatment 2 involves repairing existing delaminations and potholes and adding sacrificial anodes. Treatment recommendation 3 involves repairing existing and future potholes without adding sacrificial anodes to reduce the cost. And this treatment is recommended, or is most similar to a do-nothing approach. And it's for situations where the chloride initiation threshold has already been exceeded, but less than 5 years of service life are needed. So the potholes are repaired for safety purposes only without sacrificial anodes to reduce cost, while plans for reconstruction are being developed. Treatment recommendation 4 involves removing delaminated concrete and then scarifying and overlaying the concrete. Scarification depths ranging from 1/4 inch to just above the top mat of the reinforcement are commonly attained using a milling machine, and concrete overlay thicknesses are typically at least 1 1/4 inch. Computer modeling software should be used to ensure that sufficient contaminated concrete will be removed to prevent corrosion initiation after equilibration. And an overlay should be placed within a year and maintained through future years to prevent water and chloride ion ingress, as previously described in the discussion of treatment 1. An example for treatment 4 of deciding how much concrete to remove and replace: the chloride profile on a bridge deck may be such that removing 1/2 to 1 inch of concrete will remove sufficient chloride ions that the chloride concentration at the top mat of reinforcement will be reduced to below the chloride initiation threshold after equilibration. So this figure on the right, it looks kind of interesting just because we have a negative depth, but the horizontal bar again represents the rebar, and the negative depth represents the new surface of concrete, because it was a 1/2 inch mill and then a 1 1/2 inch overlay, or I guess 1 1/2 inch replacement of concrete, so that there was a new concrete of 1 inch higher than the original concrete surface. So you can see that after 4 years at the depth of the rebar, we're not yet below the corrosion initiation threshold, but sometime between 4 and 14 years, the chlorides equilibrate enough that the chloride concentration at the level of the top mat of rebar is below the corrosion initiation threshold. A second example, the chloride profile on a bridge deck may be such that removing 1 1/2 to 2 inches of concrete is necessary to remove sufficient chloride ions, such that the chloride concentration at the top mat of reinforcement will be reduced to below the corrosion initiation threshold after equilibration. So in this case, we remove 1 1/2 inches of concrete and replace that 1 1/2 inches. And sometime between 2 and 7 years, the chloride ions equilibrate and the chloride concentration at the top mat of rebar is no longer above the chloride initiation threshold. Treatment recommendation 5 involves partial depth deck replacement using hydrodemolition. Partial depth deck replacement can be used as long as the chloride concentration at the depth of the bottom mat of reinforcement has not reached a threshold of corrosion and less than approximately 10% of the underside of the deck exhibits damage. And after the concrete has been replaced with new concrete, an overlay should be placed within a year and maintained through future years to prevent water and chloride ion ingress, as previously described in the discussion of treatment 1. And because hydrodemolition typically removes any epoxy coating from the top mat of rebar, the corrosion initiation threshold for black bar, which is 2 pounds of chloride per cubic yard of concrete, should be used for future evaluation of decks that have received this treatment. Treatment recommendation 6 involves full depth deck reconstruction. And treatment 7 involves repairing deteriorated overlay areas if possible. And those repairs could include overlay patching, crack sealing, asphalt surface treatments, etc. And then the bridge deck condition should be reassessed when the overlay reaches its estimated service life. So using all of those junctions and treatments, we took the 15 decks that we tested and we ran them through the decision tree to make sure that we were getting valid recommended treatments. And just as a note, so I'm going to go through the bare concrete, the asphalt overlay decks, and then the polymer overlay decks. But anytime that junction D was reached, that's the junction that asks about additional deck service life needed. In this simulation, we always assumed greater than 10 years because otherwise you would end up with either treatment 3 if it's less than 5 years needed, and then treatment 2 if a value of 5 to 10 years is needed. So we always assumed that greater than 10 years would be needed. And looking at these decks, C725 had high chloride concentration at the top mat of rebar, and we needed 10 years. There was approximately 5% deteriorated, so we ended up with treatment 4. C760 was in worse condition. It had 15% deteriorated and about 2% deteriorated on the underside. And the bottom mat of rebar had not yet reached the threshold, so we recommended treatment 5, which is partial depth replacement. F562 ended up similar to C725. And then F799 and F800 both are treatment 1. For the asphalt overlay, you can see that C460 and C698 ended up at treatment recommendation 4. And that's the scarification and overlay. And then C794 and F53 were both in very good condition. The overlay and membrane were protecting the bridge deck. The chloride concentration had not yet reached corrosion initiation, and there were not sufficient chlorides to initiate corrosion after equilibration. And so they received treatment 7, which is to wait until the end of the estimated service life of the overlay before reevaluating. And F476 was not protected more than 90%. That percent low VEI being 13.5% means that 86.5% is covered, which is less than the 90% threshold. The chloride concentration at the top mat of rebar was high, and we needed additional deck service life. There was 13.5% deteriorated, and we could not see the underside of the deck, but we assumed that it was less than 10%, and we ended up at treatment 6, which is a full depth deck reconstruction because the bottom mat was so high. For the decks with the polymer overlays, 3 of them ended up at the scarification and overlay, and 2 of them were in very good condition, had low chloride concentrations, and were protected by their overlays, so they ended up at the treatment 7 to just wait and see what happens. So for a summary of our research, 23 methods of condition assessment were identified, 6 preservation and rehabilitation methods were identified, and 4 non-conventional reconstruction methods were identified. Based on the results of fieldwork and statistical analyses, the following are recommended: placing either a polymer overlay or an asphalt overlay with a membrane, either immediately or within a year after construction. That is very highly recommended. And then the things that are not recommended are waiting 5 or more years before placing an overlay, reconstructing a bridge deck using internal curing, and using automatic de-icing systems. And something that is new from this research that we have not been able to find in the literature previously is that a corrosion initiation threshold of 8 pounds of chloride per cubic yard of concrete is recommended for bridge decks with epoxy coated bar. And for chloride concentrations less than 15 pounds of chloride per cubic yard of concrete, as measured between reinforcing bars, an increase of 40 to 70% is recommended to estimate the corresponding chloride concentration of the concrete in direct contact with the rebar. And a continued focus on preservation treatments is expected to lead to the lowest overall cost. And with your support, our research group has developed new technology, including on the left, the world's fastest automatic acoustic sounding scanner, and on the right, a brand new vertical electrical impedance scanner. And the VEI scanner is the only technique that can evaluate the integrity of an asphalt overlay. And with that in mind, any questions?
Thank you, Tenley. That was very good, very thorough, and good summary of all the thorough research you've done over the past few years on this project.
Thanks.
Would anybody like to lead out with a question on any of the topics that were covered?
David, while individuals are thinking about possible questions, I just want to point out that with respect to internal curing, the qualification that's given in the report is that it is not recommended for use when precast half deck panels are underneath it. So that's a qualification that we wanted to add there.
Okay.
We welcome any questions or comments about the overall decision tree or any other aspect. I think that it's very difficult actually to think about the decision tree through a Zoom conference like this where you can't look at the entire thing easily at the same time.
I can scroll back to that if anybody would like me to.
I actually was impressed with the decision tree. It's a lot different than when we first started out. And I went over that before this meeting a little bit. So, but no, I think you guys did a good job with that. I guess this doesn't have to do too much for the report. Tell me your last little comment about some of the equipment that it can test asphalt overlays. Can you go in a little more detail on that?
Yes, so the one on the right, it's the vertical electrical impedance, and it, through water and their probe, they get an electrical connection with the rebar, and it measures the impedance, which is kind of the opposite, or I guess similar to electrical resistance of concrete. And so it measures the protection that is offered to the rebar either through the concrete above it, as well as any overlay that is in place. And so with an asphalt overlay, they can see any so-called hot spots or leaks where the overlay and membrane are not providing protection to water and chloride ingress again to the rebar.
So does it give you a probability of corrosion? Have you guys developed that, or is it just that you see potential areas?
It's just potential areas of, it's just the protection that is offered to the rebar.
Okay.
In some ways, Thad, this particular apparatus operates much like a rapid chloride permeability test. In fact, we've developed a miniature one of these VEI tests, and we've run it on cores, which takes about 5 minutes or less. And then we've compared that with the results that we get on the same cores in the rapid chloride permeability test, which, as you know, takes at least 6 hours plus the conditioning. And we have a very strong correlation. The neat thing about this apparatus, though, is it can be deployed in the field. It collects data from a moving platform. It travels about 2 miles per hour. It measures a full width of the roadway, and it gives you a map showing areas that are more protected or less protected. And we have begun to develop some thresholds based on the data that we've collected as part of this study that would enable some interpretation. For example, is the overlay leaking or not? Or is the overlay completely intact? Pretty phenomenal technology, and we were able to use that on all of the decks that we tested for this project. So it fills a very big deficiency in the literature.
Have you been able to do any proof of concept of this as far as running it over, say, an asphalt overlay deck that remove the asphalt overlay, sound it, and do repairs?
Have we done that yet? Let's see.
Was Wendover, did they do VEI on Wendover?
Yes, we did. It wasn't this full multi-channel apparatus. In fact, Becky was there in Wendover where we did the initial VEI testing, and then the asphalt was removed, sounding was performed, patching was performed, and then a new overlay was placed. But I don't think that we had a chance to go back and do additional VEI testing. The proof of concept that we've done for this was funded through the National Cooperative Highway Research Program. And through that program, we did extensive testing on conditions that were known and then other conditions where we could explore. And we have a full report that's separate from the report that Tinley has authored, that's strictly on the vertical electrical impedance apparatus with a lot of field and lab work both.
Does a lot of that include ones with asphalt overlays on it, or is it mostly bare decks or polymers and that type of thinner overlay?
We included all of those. We have polyester, polymer, concrete. We do have several with asphalt. And the reason for that is because we also had funding from the Nebraska Department of Roads, and they are currently accelerating the use of asphalt overlay systems with membranes. And so they invited us to their state where we did testing on 3 bridges of interest, and one of those had asphalt overlay.
So did they, I guess what I'm curious about is whether there's been any overlay mapping done showing what the vertical impedance was showing as far as locations of loss of protection versus what's actually delaminated.
I see. No, that's a great question. That relationship was done at only the Wendover Bridge. That's the only opportunity we've had to do sounding on the bare deck after the asphalt overlay was removed. And in that case, we had a very high correlation. In fact, there was a delamination normally within 1 or 2 feet of every place where we had low impedance. So that was a very, very good correlation.
Do you have that Wendover correlation? It's been so long. I'm sure somewhere I've got it, but it would be interesting for us to revisit that and take another look at it.
Okay, I think we published that in an ASCE venue. I'll go back and look and see if I can forward you the paper. The underlying requirement for that is that the deck needs to have been in that condition for some number of years, right? If for example, a bridge owner put a brand new overlay on an old bridge deck without making any repairs, then the VEI apparatus would suggest, assuming there's a membrane, that the deck is very well protected and would predict no delaminations, even though the delaminations are there present underlying the asphalt overlay. So the idea is that if the bridge has been there in its current state for a number of years and the leaking asphalt overlay has allowed chloride ion ingress over a number of years such that there is now delamination, then you would get very good correlation. And that's what happened in Wendover.
Okay.
Yeah. I'll make a note to look for that report for you.
Do you have to saturate the surface or just mist? I mean, 'cause it looks like it's wet in that picture, but I mean, do you have to saturate, let it sit and kind of try to find all its little cracks and crevices before you run the test? Or is it wet as you go type of thing?
No, great question, Thad. In the very, very top of the picture that Tinley has posted right now, you see a water tank positioned in the back of the truck. And we have an automatic sprinkler system so that as we drive, we saturate the deck surface. That is important because we need to be able to establish electrical contact from the VEI probes down through the deck surface. And consequently, not only does this become a wonderful crack finder, for example, when we tested the Ogden 24th Street bridge deck, the cracks on that bridge deck, especially the transverse cracks, showed up beautifully in the VEI map. And so not only does it end up showing us the cracks because they leak and they're low VEI, but it also ensures that we get continuous electrical connection to the deck. And we do this, by the way, without drilling into the rebar any longer. When Becky was with us in Wendover, we had to drill into the deck and connect to rebar. We've now developed a patented approach that completely eliminates any requirement to drill into the deck. And this is a very large area electrode, which is what you see kind of in the center of the frame, in the front and the back behind the row of smaller electrodes. So very convenient now.
My other question is not related to this, but it was I thought it interesting what you guys were talking about when it comes to the chloride sampling between the bar, which we normally try to do a lot of times so we're not hitting the bar,
Right.
and also at the bar. How did you guys correlate those two in sampling to come up with that? Or give a little more background, if you would, please.
So where we had the two test locations that were co-located, 1 and 2, and then 7 and 8, we drilled directly over the bar and collected our samples directly over the bar. And then within about probably 3 inches, maybe edge to edge, maybe 4 inches center to center, we drilled again. And then using the cover depth that we know what it is because we hit directly on top of the bar, so we know the depth of the top of the bar, we interpolated the chloride concentration between bars at that exact same depth and then compared those two, and that's where we found the increase of 40 to 70%. So I can actually, I guess I can pull up that graph again.
It makes sense because, I mean, the moisture is traveling along the bar path of least resistance, but I mean, I haven't heard that claim before. And
yeah, the physical presence of the bar acts as a barrier to the chlorides, so they kind of build up a little bit before they start kind of sliding off and diffusing to the sides. So this figure on the left, so the y-axis is ratio of above to between, and then so it's numerator and denominator, and then on the right would be the denominator, or the chloride concentration between the bars. So there are some that are maybe not quite that high and some that are really low, but you'll notice that those are at the really low concentrations where they may not have had as much of a chance to build up. But a majority of the points are above 1, and our linear regression shows that it's between 70% at the low end down to about 40% at the high end. I guess I should say high chloride concentrations.
How many samples did this come? Do you have here? I'm trying to count.
It would be somewhere between, let's see, we had between 50 and 60, I think.
So you have quite a few samples to correlate to. Okay.
Because we had 2 points at each deck. I guess it would be between 25 and 30. And there were a couple
points on that chart, right?
And there were a couple instances that we tried to hit the bar and didn't hit it on either of the locations, and so those data are not included here. But a majority of the time we hit bar twice. We hit the top mat of bar twice, and it's compared here.
And these were all done with the drilling and, I guess, in place rubberization of concrete is what
exactly
for all these tests.
Yeah.
Yeah, in fact, I'm not sure that this kind of an analysis could be successfully performed unless you have the ability to really dial in directly over the rebar and then isolate away from the rebar just a few inches. So that technique was critical for establishing this relationship, and that I'm glad you brought some attention to it. In almost every paper that is available in the literature, the physical presence of rebar is ignored. And yet we see from these data that the physical presence of rebar enables for an accumulation of chlorides over the top of it before they finally build up to a point where the equilibration forces them to go around. And consequently, in fact, this chart shows that sometimes the chloride concentration right over the bar might be even 3 or 4 times higher than what you would expect between the bars. And it just depends on kind of the age of the deck and the exposure of the deck. As the deck gets older and older, so that it's been exposed to more and more chlorides, both between and above the bar, at the depth of the bar, we start to see some approximate ratio. You see how it kind of converges on 1 the further out you get. And so, but early on, like in that first 15 years, this ratio is significant. And so by drilling only between or sampling only between bars, we may be underestimating the actual chloride exposure considerably. This is brand new information to the industry.
Is your data, the raw data in the appendix of the report,
Yes.
your chloride samples?
Mm-hmm. Yeah, there are a lot of tables in the appendix of the raw data. We have a lot of data.
Yeah, I'm actually flipping through it now, just trying to make sure I see it. But do you distinguish in the table whether or not it's over the bar or not? I was trying to.
I think there should be. Let's see. It should be Appendix B, and it's like starting with table B16 is where it should be. So if there's an asterisk next to the number, that means that we hit the top mat. And if there's a double asterisk, it means we hit the bottom mat.
Oh, that's in the, it says that in the beginning of the appendix. Okay. Thank you.
Yep.
Thanks, Thad. Any other comments or questions?
I've got maybe a couple. Looks like Becky wants to. Did you want to go first, Becky?
Oh, I was just going to say, and I know we've talked about this before, I guess I'm just still a little concerned with the kind of heavy focus on recommendations for asphalt overlays. That's what kind of the data is saying. It's just not really in line with what we've been seeing in the field and in practice. So I don't know, just still a little leery of that.
Well, and our recommendation is that it's just a recommendation, but when we get to where we're recommending an overlay, that is based more on other things rather than like it's just if there is asphalt on either side of the roadway, if it's an asphalt corridor, that would probably be the only time that we would recommend an asphalt overlay. We wouldn't expect an asphalt overlay to be placed in a concrete corridor. But the data that we found, I guess the results would be, is that there were some pretty low chloride concentrations on the decks that had them placed immediately. On the decks that they were placed later, usually it's like more than 10 years, then we did not see as good of results because the chlorides are already in the deck. But when they were placed immediately and they had a membrane, we found that they kept the chloride out. F53 is one of those examples. Oh, sorry.
I think one of our concerns with the asphalt overlay, Timley, is even though the adjacent roadway may have asphalt on it, we get load rating concerns because they build up the adjacent roadway and they don't really consider the deck because all they see is a flat road. So they just kind of pave over everything, which then affects our barrier heights. It affects our load rating. And then eventually, and this is where we're seeing a problem in some of our interstate corridors where they originally had asphalt, they come back and they build the roadway back with concrete at the existing elevation of the asphalt.
Oh, I see.
And so what happens, we now have a pan at our structure where our structure itself still has the 3 to 4 inches of asphalt, and they've built concrete roadway up to that elevation. So all the water now, because your asphalt is more pervious than your concrete, it's all being stuck in that pan. And we're seeing a rapid rate of deterioration in those bridge decks. So I think that's where I still kind of say, you know what, even though we have adjacent asphalt roadways, I don't like the idea of saying it's a good idea in this situation, because looking down the road, what type of impact it has on potential impact for the structure.
I see. So in terms of maintenance, it may not be the best idea, but yeah, I mean, given the data that we had, that was what we based our recommendations off of.
No, and I understand that a membrane of any kind is going to improve or reduce the possibility of chloride ingress into the deck. And so I can see where, asphalt overlay with waterproofing membrane does assist in that. But if I'm looking at trying to determine a decision matrix of what to put on my brand new deck, I don't think asphalt should be considered at that time. I see asphalt as being more of I know my bridge deck is going to need to be replaced in the next 10 years. I'll put asphalt on it as kind of a temporary Band-Aid that kind of holds it all together, and I can nurse it along for 10 more years until I have that project in place.
Would it be okay with you if we include some of these anecdotal pieces of information that you just shared in our report? Because we could indicate some of these reminders to the user. If later somebody is reading this and they see the recommendation, they might want to know all the constraints that should be addressed. Would that be all right if we also list your name, like as personal communication?
Yeah, sure.
Okay, thank you.
I think that would be really good, actually.
Yeah.
So the other consideration that doesn't come in here is we have a lot of phased construction, and we have seen when these membranes are placed in phases, they do not do as good a job in creating a seamless barrier. So,
that's a good point, Cheryl.
Some of these older ones, we didn't have the same traffic limitations. We also had different products being used for the membrane, and we are seeing now that they are not performing the same way.
Thank you, Cheryl. I made a note about that as well. Great input. We hope that the final product has all of these key considerations so that someone tracking through the decision tree and ending up with a recommendation could then check it, right, against kind of a checklist and say, yeah, this would work, or, oh wait, we have some concerns maybe about barrier height, for example. And then that would lead them to more carefully consider and maybe choose an alternative but equivalent product.
Yeah, and I think part of what Becky's concern is that what our manual says is that we don't use asphalt unless it's sort of an end-of-life treatment. And so we don't necessarily, for Utah, want our preservation manual to say that we should, because we know that it doesn't. But I understand bringing in what you've found from the research with the caveats for UDOT's preferences and experience.
Right. Well said.
And I guess I'll just finish off by saying, not to harp on this one area. I think you guys have done an excellent job, and I think it was very well presented. I think once we start using the decision tree, that'll really give us some more opportunities to see how it works. But really appreciate your efforts.
Thank you. It's been a lot of work.
Can I ask a follow-up question on that topic about the decision tree? This is David. And maybe it's more for the UDOT group here, but how do we foresee using the decision tree, or maybe this entire deck management guide in UDOT practice? Is it something that would need to be kind of folded into an existing manual that UDOT uses, or an existing decision tree or matrix of sorts in I don't know if it's in a spreadsheet format or another software, or is that still kind of in its infancy on outside of the research also?
Becky, do you want to take that first, or you want me to throw something at it?
Sorry, it's kind of loaded.
Before Becky hops on, one thing that I was going to say is I kind of want to play with this decisions tree a little bit in our planning perspective of seeing how it aligns. I've looked at it and looked over it, but here we've got percentages and stuff like that, and I want to see how it compares to what we're actually have been doing and what we are, I guess, planning to do, and see how that lies with it. See if any tweaking needs to be done.
That's completely in line. What I was thinking is we would probably pilot it first to see how it works in practice. And then as we test through it, it would be adopted into one of our manuals.
Yeah, what I was kind of thinking, quite a few preservation projects that we're working on scoping right now. And I think it would be interesting to go through the scoping of those, of kind of what our current practices are. And then after we get through those scopes, to then go back through those same bridges and run them through the decision tree and see how that aligns with what we're doing as our current practices.
That would be a really interesting comparison.
Mm-hmm. Yeah, and then, I mean, maybe from there we start looking at making some shifts to what we're doing on the recommendation too, as we're getting ready to program them.
And we know that 15 decks and the literature may not be the perfect representation. So we expect that there may be some kind of tweaking along the way of maybe certain values of what may be better in actual practice.
I think also something that needs to be considered is, I mean, I'm sure with your research and developing of the tree, you didn't consider cost. And I think sometimes that's in a planning group, we have to look at that as well. I mean, it would be nice to do a hydro demo on every structure possible.
Right.
To extend, you know, that falls within that realm, but it sometimes may need some other treatment instead, just because we don't have the money to do that. Or same with polyester. And so, but I know you put a lot of effort, and I echo Cheryl's comments. This has been a big project, and I know I've seen how it's developed and changed. And so I really do appreciate the effort that's been put into it, and I've been excited to see the results of it. So thank you.
Thanks.
Thanks, Thad.
Well, I'm glad to hear that it sounds like it's going to be very useful to UDOT, and that we're looking forward to utilizing the results and recommendations in the decision tree that's been presented. Sounds like it might further develop and mature over time, which is great. Maybe a follow-up question on that is the research format, I mean, the research report format, and I don't know if we have really resources to change any of this, but is that a format that is readily useful, or is it going to take some effort for UDOT to kind of transfer that into maybe a tool for design teams or for planning purposes?
David, I'll just comment. We've tried to lay it out with the user in mind, so that when UDOT is ready to finalize that decision tree structure in a manual, that they would be able to simply copy and paste the schematic, like the diagram portion. And then also we have very clear descriptions of each junction that could be copied separately. And that way you can separate the really like day-to-day useful decision tree from the extensive literature review, for example, that also is included in that report.
The only thing that I would recommend with that decision tree is when you say continue to a certain junction, is you have that junction a certain color. I know I'm going to color here. And then have that junction also the same color. Does that make sense? So, because one thing when I was going through it, I was trying to find, okay, it says continue to junction H. And so I'd be scrolling through the different cables, and I understand you have to kind of break it up to several pages, and trying to find that junction. But if there's something that would be color related or something like that, where I visually can see the difference and say, okay, I now need to be here, to me, that would be a assistance.
I think that's a good suggestion.
Yeah, Tinley and I actually discussed the potential use of color in a previous iteration of it, and decided that we would stay with black and white for the research report because it's more easily copied for distribution, and it's easier to print without shading. But I think at some point it would make sense when we're ready to finalize it to have color coding so that, for example, junction H is always a certain color regardless of which page it appears on. And you could even have some shading behind the text that describes junction H, same color. So it's all color coordinated and easier to look at.
And we could
David,
also, oh, sorry, go ahead.
David, on that note, are we requiring still printed documents instead of electronic?
With our research reports, no. I mean, we can provide printed copies.
No, I'm going the other direction. If it's all electronic and PDFs, then we don't have the issue of needing black and white for copies.
Right. Yeah, we aren't relying on that right now.
Yeah, it's still many of the journals where we would later try to publish something, they are still asking for no shading, no screens, they call it, over figures or tables because of the same issue where they don't print in color. It's difficult for then others to access. So anyway, in the broad scheme of things, when we're trying to develop something, we're just trying to make it as helpful as possible for the given format. I think the best way to move forward when we're ready is to create a special manual that redoes the formatting. And I know sometimes even for manuals, a different font or different font sizes that would not be typical of an academic or research report could be used with more graphical design. And we've stopped short of trying to do that, focusing more on the technical side and making sure that the thresholds and the structure were correct. I think there's a really great path forward, though, to really make it useful and easy to read.
Well, that sounds really good, Spencer. I'm wondering, was that planned all along? Is that part of this research effort, or are you talking about down the road that UDOT would actually go and do that, or are you offering to do that?
Well, it's not included as part of the current scope, like to do the graphical design and produce a separate manual, but we would definitely be interested in doing that when UDOT is ready to have it funded. In fact, I think that it would be appropriate in some number of years, maybe it's just 5 years, to go visit some of these bridges again, many of which I'm referring to the 15 that Tinley showed data for. Many of those received a treatment immediately after we tested it. So for example, I think F53 was one of those that was under construction, and as soon as we left, the asphalt overlay was removed.
F562 and C725 have received PPC.
Mm-hmm. And one of these I thought had a hydro demo.
I think C757, 759, and C760 all had hydro demo shortly after. They were the Knudsen Corner.
Right. So some of these have already had an interesting treatment that may or may not have been consistent with the final recommendations from the decision tree, but we didn't have all of the data that would have been considered. For example, how many years of service life it was an assumption that we had to make. But it would be very interesting to go back and look at chloride profiles to see, have they equilibrated as we predicted? Or do we see now that the corrosion activity is reduced, and look for any evidence of delamination? So it could definitely be a study that happens in a few years where we give some time for these treatments to take their effect, and then we would perhaps refine some of the thresholds or other aspects of the tree and make a proper like UDOT manual that's different than a research report format.
Well, it sounds like a good idea. I imagine the structures group here would want to discuss that further for what they're comfortable with or what their needs are.
Mhm.
Looks like our time's winding down. Does anybody else have more questions for Tenley or Dr. Guthrie regarding this project? I have maybe just hopefully this is just a quick one. I don't want to go longer than we need here, but I was curious about the thing you were talking about when there's a hydro demolition and there was epoxy coated rebar, but then you consider it as black bar after that, after they put the concrete over it in that rehab process. And then it suddenly needs a different threshold value for initiation of corrosion. So it goes from 8 down to 2, I guess is what you said, for the value for threshold. Is that something that is in the literature, or you're recommending that as a kind of a new feature here, or is that something UDOT has been aware of and implementing on projects, or maybe we haven't had hydro demolitions long enough to be able to consider that?
Mhm.
I don't think that is something I came on in the literature. Dr. Guthrie and I remember sitting in his office and just kind of came to that realization that I think we may have been looking at some pictures, but you can see in photos after hydro demolition has been done that a majority, if not all, of the epoxy coating has been stripped just through that process. And so that protection is no longer there after the new concrete is in place. And so it's just something to be aware of and keep in mind that even though it may have been constructed with epoxy coated rebar, after the hydro demolition is done, that top mat no longer has the epoxy coating.
Yeah, those hydro demolition jets operate at pressures exceeding 30,000 psi, and it strips the epoxy coating right off, except for the little strip at the very bottom of the rebar that may never have been exposed to the direct shot from the hydro demolition jet. And so this emphasizes the importance of keeping the surface of the deck sealed using, for example, thin bonded polymer overlays or a PPC after hydro demolition and then the placement of the new concrete, because the epoxy will no longer serve any kind of purpose.
Okay, well that makes sense. It's good to have it documented here as a kind of something to consider going forward. All right, any final questions before we wrap up and move on to other exciting meetings or activities? Okay, well, I'll go next to say thank you so much for all your hard work on the project and also for taking time to go over with us today. Look forward to the final product of the research report. I think you're still doing some revisions on that, but we'll communicate on that over during this month and hopefully wrap it up. I think at that point, when we get maybe that near final version, we can decide whether we need all the TAC members to do thorough review again, or if you want to point out certain areas that need some review. I guess I'll be looking to you and perhaps Cheryl and Becky for guidance on whether we need to do full review. It's just such a large report.
Yes, it is.
Yeah. Thank you, David. We can certainly do that. I've taken some notes. Tenley has also, during our presentation, will incorporate this input to the report and send it back to you as soon as possible. We really appreciate the support that UDOT has provided us. We feel like this is a significant contribution to the literature. We feel like we've been able to put together in one place what amounts to literally hundreds of references and separate ideas that are now all in a synthesis. And we feel like this also enabled us, after identifying some of these deficiencies, through other funding to develop new equipment, for example, that now is available to UDOT here in the state. So we really appreciate the funding and the support and the opportunity to study this. If we understand correctly, UDOT is the very first state in the United States to have created a concrete bridge deck management guide.
At least one that is this comprehensive, for sure.
Mhm. So thank you again.
All right, well, with that, we'll close. Thank you again, and thank you everyone for participating. Feel free to follow up with Dr. Guthrie with additional questions or feedback on the report or today's presentation. Thank you all.
Thank you.
Thank you very much.
Thank you.
Thank you.
Thanks.
Bye-bye.